I'm the Speciation chair. I'm also the first speaker, Danny Worker. And today I'm going to be talking about my work on how range overlap drives chromosome inversion, fixation, and passerine inversion. So I really want to impress upon you that the fact that the process of speciation involves not just the accumulation of molecular changes in DNA composition, but oftentimes also the large structural rearrangements of the architecture of divergent genomes. So chromosome inversions are one type of structural arrangements that are often found as fixed differences between species, as well as polymorphisms that are segregated within species. And despite the near ubiquity with which inversions are found in nature across all study systems, their association has been implicated in roles like modification, reproductive isolation, sex chromosome evolution, and superevolution. We still know relatively little about the actual evolutionary forces guiding a new inversion's loss or fixation. So, in the system I work in, birds, chromosome inversions are also incredibly common. And more recent comparative genomic studies have found hundreds of inversion differences across a whole range of sizes between distant abilities. But there's actually a really large cytological literature that's been studying the karyotypes of birds for many decades. And this is the work I'm going to be drawing upon from this talk. And so a karyotype like that of the finch shown here, there is a lot of information content in it for large structural rearrangements. For instance, if you were to look at a simple trait like centromere position of the chromosome, when you compare between different species and the centromere has been relocated, if it's associated with banding pattern reversals, these are indicative of paracentric inversions, inversions that contain the centromere. And so if you compare the karyotypes in centromere position to different species, say of this starfinch and closely related confamilial to the painted finch, you compare the karyotypes of these in terms of centromere positions, you can find evidence of paracentric inversion differences. So for instance, between these taxa, the Z chromosome, the W chromosome, the second chromosome, the sixth chromosome, as well as the seventh largest autosomal chromosome, all have centromere relocations indicative of paracentric inversion. So the guiding question really that I'm interested in, that's motivating the study, is what evolutionary forces underlie chromosome inversion evolution? Why do some groups involve more inversions than others? And how do chromosome inversions spread? And so traditionally, traditional models of inversion fixation by genetic drift rely on heavily structured populations, inversions being underdominant and selected against until drift acting within small teams brings them above 50% frequency, after which selection favors and spread execution. In contrast, selection can directly favor a new inversion. For instance, if the breakpoints of the inversion itself favorably alter gene expression, or if the inversion is associated with meiotic drive elements, can be selected to spread. More recently, there's been a focus on the contextual selective advantage that the new inversion has as a recombination suppressor. So when an inversion is in the heterozygous state, it's a powerful suppressive recombination. And contextually, there's a big advantage for inversion if it contains and keeps linkage between extrinsic differences between hybridizing populations, like ecological differences between populations, or intrinsic differences involved in reproductive isolation. And these alternative models can be compared because they make different predictions about the associated demographic correlates of inversion fixation. For instance, drift models are largely population size independent because the dual effects of population size of the production of the new inversion and the fixation probability of the new inversion cancel each other out. In contrast, all adaptive models are highly dependent on population size because we're talking about mutation rates. Larger population sizes, more inversion events. However, recombination suppression models have this added influence where you need gene flow. There needs to be gene flow between differentially adapted populations, incipient species that's deleterious but provides a slight advantage. And in contrast, these breakpoint selection meiotic drive models are really, really dependent on population size, more so than no contribution to gene flow because they rely on mutations of large effect, which you're likely to compare. And so a recent study by myself and Trevor Price looks at the phylogenetic distribution of paracentric inversions in one family of birds, the finches, rate of inversion fixation within consonant groups was threefold faster than island groups. And what's the difference between island radiation and continental radiation? We found that both range size and range overlap are much greater within consonants. So range size of birds or most species, larger ranges, more individuals, larger population size. And range overlap, when we're talking about closely related species, this is the impetus for potential for gene flow between them. So if you have a lot of closely related species that are overlapping, gene flow is possible before reproductive isolation is complete. However, we didn't have a sample size to really disentangle the relative contributions of range size and range overlap. And so today I'm going to be talking about a dramatic expansion of that previous work to the entire passerine radiation. So the passerines are one order of birds, but they comprise over half of all total species, some 6,000 species, some of the more iconic individual taxa that are represented here in this beautiful painting from Julian Wasserman. And we also have the benefit of the fact that a lot of these species have actually been karyotyped. So some 410 passerine species have had their karyotypes described in the same way that I showed you with the painted starfinch. This is about 8% of the total extant taxa. And so what I did, similar to the Australia study, is look at centromere position for the 9 largest autosomes and both of the sex chromosomes, the C and the W, and for each species contributing to a characteristic matrix of centromere position for these 11 chromosomes of interest. And so chromosomes, in the chromosome literature, you can define a chromosome based upon the ratio of the long to the short arm, and this is the character that I'm modeling. I then, because I wanted to put these inversions into a phylogenetic context, I built a new phylogeny for all karyotype species shown here. I built this with 2 mitochondrial and 4 nuclear loci, and actually time dated it with 20 different fossil calibrations to get a time dated tree. This is actually the most rigorously calibrated passerine tree to date. And then I used a maximum likelihood approach to infer the inversion fixation history upon each branches. So estimating ancestral centromere position across all nodes to infer on which branches inversions have fixed. And so when this is done, sorry, it's a little gnarly, but so this is the tree with branches color-coded by rate of inversion fixation. And on the left-hand side here are the 59 passerine families that are represented. And within the brackets, we've got the number of species within those families and the number of inversions that have occurred within each of those families as represented. And what should hopefully impress upon you is there's an extreme amount of rate heterogeneity of inversion fixation within the passerines, and this is what I want to help explain. And so I looked at chromosome inversion evolution at 3 scales across clades, sister species pairs, as well as species triplets. So to start with, I looked at 80 clades. So I divided up the tree into clades that had at least 2 karyotype species within them, were representatives of the radiation of a contiguous geographic area. So all individuals within that clade were in Australia. They were all ecologically similar to each other, all finches, all warblers, etc. And across these, I included non-karyotype as well as karyotype species, because the forces going on here are not limited to karyotype taxa. So I'm taking demographic data from all extant species, and I figured out which species belong to each clade from previously published level phylogenetic studies. And so for each clade, I counted the total number of inversions, as well as the amount of time that's represented in each clade, so that's the total branch length of the karyotype members of the clade. To get at this population sizing, looked at median range size, breeding range size for the members of that clade, as well as median body mass for the species within that clade, to together account for population size variation across clades. To get at the gene flow, I'm again looking at range overlap. So this is looking, I assigned a range overlap score as a proportion of sympatric species pairs within each clade. And this was arrived at from doing a pairwise matrix of all member species, and if they overlapped by more than 20% of their breeding ranges, that was scored as sympatric. And then I also included like a very broad description of ecology, where each clade is defined either as being granivorous, herbivorous, insectivorous, omnivorous, just to see if there's any difference between like the way that a finch speciates with inversions as opposed to a warbler. the number of inversions with respect to these traits within each clade. And what I found is that the best supported model for the number of inversions in a clade included 3 parameters: branch length, range overlap, and range size, but only range overlap and not range size was found to be significant. So the upshot here is that if you look at the x-axis here, proportions sympatric species pairs within a clade, each dot corresponds to a clade. The rate of inversion fixation on the y. Clades with more sympatric species have more inversions. And then just to take a representative example of opposite extremes, contrasting the grassfinch radiation and the parrotfinch radiation. Both of these are stroled groups. About the same number of species, about the same crown group age, but they differ significantly with respect to proportion of sympatric species pairs. Most grassfinches, or a lot more grassfinches, overlap with each other. Parrotfinches are mostly all Patrick. And we also find there's 3 times as many inversions within grassfinches compared to parrotfinches. 1 every 2.7 to 1 every 8.3. And so range size was not significantly associated after including these other parameters. However, there is a positive association still, just looking at the low between median clade range size and inversion fixation rate. Speed up a little bit. There is no obvious association of ecology with rate of inversion fixation. So these points are color-coded by the thinning of ecological groups, indicating that at least in this broad context of handsome groups, there's no difference. So I also looked at 47 sister species pairs in a similar way, counting the number of inversions, differences between sister species, the age of that pair, the average range size, and a binary trait of whether they overlap, whether they're sympatric or allopatric. And I also included more directly look at gene flow, whether they're known to hybridize in plants. And similar model comparison type of thing, I found that the best supported model explained the number of inversion differences between sister taxa includes two factors, whether they overlap in range or not, and the age of the sister group. But the only significant factor here, again, is range overlap. Whether they're sympatric is the most important factor. And then, so looking just at this as a proportion, so these, the proportion of sister taxa that have an inversion and don't have an inversion, you can see that significantly, sympatric sister species are significantly more likely to differ by inversions than allopatric ones, and to have more total inversion differences than allopatric ones. And when we look at the subset of sympatric species that are actually known to hybridize in wild, we maintain this difference in terms of the likelihood of differentiation by inversions and the number of inversions. And the critical thing here is that though sympatric species are older on average than allopatric ones, which is not a surprise, the hybridizing ones are not. So age is sort of accounted for here. And very quickly to finish, I also looked at these species triplets. These species triplets are a powerful way of completely controlling for age. So a species triplet is composed